So the work done by the external force is equal to, so I'm going to cut to the chase, there is meant to be a dot product right there. So the external force is outwards and the displacements are all outwards. So they're parallel vectors, and the dot product between parallel vectors comes with a plus sign, and it's just the product of the magnitudes. So this goes from R1 to R2, G, mass of Earth, mass of the moon, divided by r squared. That's a varying radial distance, right? That is the external force applied. Here, it's just the opposite of the gravity force. The gravity force was always backwards, but the external force is always outwards towards the right. Integrate along dr's. The dot product is, okay, so before I continue, I expect that the work done by the external force is positive, right? This is what I expect. So if I go up here and finish this calculation, what's crazy is I've got this 1 over r squared dr, and when you integrate 1 over r squared dr, you get minus, right? So all of a sudden there is this weird minus sign from the integral. And then inside is 1 over r evaluated from r1 to r2. So if you calculate, or if you finish what the bounds go to, it goes minus g, mass of Earth, mass of moon, times 1 over r2 minus 1 over r1. And then if I go to the next line, let me put this minus sign in here, so it just switches the order. It goes g, mass of Earth, mass of moon, times 1 over r1 minus 1 over r2, like this. And remember, we're moving the object outwards, which we expect is a positive amount of work done by some external force. So let's make sure this is positive. What's strange is r1 is smaller than r2, because r1 is the inner position and r2 is the outer position. So it looks like we have a small thing minus a big thing, which should be negative, which is backwards, but that's not actually the case. r1 smaller than r2, which means that 1 over r1 is bigger than 1 over r2. And this guarantees us that if r1 is smaller than r2, then the work done is positive. That's what I wanted to show you. So let me go on now. So we discovered that the work done by an external force, where there was no change in kinetic type energy, the work done by an external force, if the kinetic energy doesn't change, is actually what we call the change in the potential energy. In this case, we're talking about a gravitational potential energy. And I'll tell you that gravity forces are conservative. Takes a little math, but you can show it. So it takes a little work. If you want to go and check that gravity is conservative, it takes a little work to go do this. But I'm just going to tell you that they are conservative. So we can define a potential energy. And if you remember, the change in the gravitational potential energy is equal to the work done by an external force in the situation where you don't change actually any other type of energy. And when we talk about mechanical energies, so the only other kind of energy besides potential energy is kinetic energy. So the point is we just calculated that the work done by an external force is equal to g, mass of Earth, mass of moon, divided by, not divided by, let's put in multiplied by 1 over r1 minus 1 over r2. And we're going to say that this actually is the change in gravitational potential energy. All right. So this is a big deal. The work done to move, say, the moon away from the Earth from position R1 out to position R2, that work done is very physical. There's no ambiguity. So check this out. What if I said that there was a way to describe the gravitational potential energy as a function of R? So these are two particular places, right? This is the bounds in a definite integral. We imagine these are definite locations. This here, though, is a variable location. I'm trying to imagine the case of writing down an expression that varies with this variable. So what I mean by this is I'm going to define something called the gravitational potential energy, not the change in gravitational potential energy, but the gravitational potential energy itself. And I'm going to define it this way. It's going to be G for the Earth and the Moon, right? It's mass of the Earth, mass of the Moon. But I'm going to essentially just define it this way with a minus sign. And I'm going to show you, this actually is not something that you're remembering at this point. But anyways, I'm going to show you something interesting. So U sub G at R1 is equal to minus G ME MM divided by R1, and U sub G R2 is equal to minus G mass of Earth, mass of Moon divided by R2. And the change in the potential energy that we calculated up here is equal to the potential energy final minus the potential energy initial, which must have been the potential energy at R2 minus the potential energy at R1. So that's what delta U sub G is. If I go in and calculate this difference now, I've got it here and here, this is equal to minus G M Earth M Moon divided by R2 minus, right? So there is this minus sign, and then the other minus sign is in the definition. So minus minus G mass Earth mass Moon divided by R1. This is equal to G mass Earth mass Moon times 1 over R1 minus 1 over R2. That is, if I define this potential energy as the potential energy at R, then I can use it to understand differences just fine. It gives me the correct difference. The point is the following thing. What if U sub G is equal to minus G mass of the Earth, mass of the Moon, over R, so this is the potential energy as a function of R, plus 250 joules. So this thing right here is super arbitrary. But let's see what it gives us. So delta U, gravitational energy, is equal to U sub G at R2 minus U sub G at R1, right? That's what delta U sub G is. And this is the physical thing. And I just did this like non-physical, arbitrary, no rhyme or reason choice. Right? It's non-physical choice. But let's go nonetheless use this new version of potential energy, or alternate version. So U sub G at R2, I just go fill in for R2. It goes minus G, mass of the Earth, mass of the Moon, divided by R2 plus 250 joules. That's at R2, and I'm going to subtract the value at R1. The value at R1 is minus G, mass of Earth, mass of Moon, divided by R1, also plus 250 joules. And you can see what happens. This 250 joules, and I subtract off the same arbitrary non-physical choice. This is the sense in which it doesn't matter. The constant, no matter what constant you put here, constant of integration, no matter what you put there, you'll always get the physical difference, where the physical difference is based on how much work you had to do to cause the change. Yeah, so this becomes GME massive Moon times 1 over R1 minus 1 over R2, which was the work done by an external force. This is, this is physical here. This is very physical. It's physical in the sense that in order to do a certain amount of work, you have to use a certain amount of gasoline or absorb a certain amount of sunlight into a solar panel, right? This 250 joules, there's no physical process that this 250 joules is associated with. So it's an arbitrary non-physical choice. It amounts to a choice of 0 for gravitational potential energy. Okay. The minus sign is very important. In fact, you could imagine drawing the graph. So this is when the potential energy is 0, right? The vertical axis is potential energy. The horizontal axis is separation distance. So the separation distance is here. Here are the mass values of the two objects whose potential energy, gravitational potential energy we're studying. That's the universal gravitational constant. And this graph looks like this. There is what's referred to as an asymptote. It has asymptotic value 0 as r goes to infinity.